Um, Today we're doing chapter 16, which is the formation of stars. Um, how do we get from gas and dust in the universe to a star that's fusing hydrogen into helium? So, how about where they form? Where do we see them? And out in space, in between the stars, is large clouds of dust and gas. Um, and we can observe them by their effects on stars. Um, in between stars is what we call the interstellar medium. It's a fairly low density medium. Very few particles per cubic inch or cubic centimeter. In some areas, and it forms sort of a cloud of gas and dust. In this picture, we can see some different versions of these clouds, what end up being what we call nebula. And in places where it's red, you're seeing light from hydrogen atoms. The gas is being warmed up. In places where it's dark, you're seeing the gas and dust absorb light rather than emit it. Bluish glows are reflective. Their light is reflecting hot stars' light off of the cloud of cool gas. And, you can see some of the other features here. There's other stars that is putting out into helium, and you can see clouds that are surrounded by gas and dust, and so lots of different versions of this. And here's another version. We can see emission as red light from ionized hydrogen, and then the blue light that we see is reflection of blue light from the clouds, and the dark areas are absorption. So this is how we can tell that there's material in between stars that can affect the light of stars. And in particular, we can look at the spectra to figure out what elements constitute the gas. And it's an awful lot like gas as a whole in the universe. It's mostly hydrogen, a little bit helium, a little more helium than you think, because this will tend eventually to be stars, so they're enriched in helium. And there'll be heavier elements for the same reason. But we can pick out from the spectra absorption lines that match up to the elements that are in the clouds. So most of the matter is fairly cool. Individual groups of atoms that are very low density would be like 3 to 10 Kelvin. But these higher density bits of star-forming clouds are going to be molecules at about 10 to 30 Kelvin. And it's going to typically be very simple molecules. Hydrogen, helium tends to just be lone atoms. You'll get oxygen, nitrogen, carbon monoxide, just one or two atoms bolted together. We'll get other stuff. You hear reports every once in a while that they found ethanol or formaldehyde or even amino acids. They find complex molecules. But for the most part, very simple molecules of just hydrogen, carbon, oxygen, nitrogen. And, the density is going to be a few hundred molecules per cubic centimeter. This is a high density, comparatively. This picture comes from a particular... if you look at the northern sky, you can see this region, and you can see what this would be, which is basically not much. You're looking in the naked eye, you don't see as much detail. Going back very quickly, this, if you go look at the night sky, this is the constellation Orion, but for particular stars in the constellation, you can make out that they're not really stars, they're a nebula. So this is a very small portion of the Orion Nebula. Above is going to be the belt, and then the sword hangs down, and there's going to be this region in here is going to make up like one star in that constellation, or one. So most of our understanding of molecular clouds is oddly going to come from carbon monoxide in the cloud. The emission lines from it tell us something about how the cloud ends up forming stars. So here's Orion again, belt and sword, and the image I was trying to show you is here at the bottom middle of the sword. In visible light, it looks like a star. In infrared light, it becomes clear this is a much larger body, but at the core of it, here is what we'd call the Orion Nebula. But it's a very large, region, several different nebulas, several different star-forming clouds. Right, so Orion is down here at the end of the sword. Horsehead is in the middle of the belt. I think up here is the eagle, but that's not labeled here. Several different nebulas visible. That's detectable here. So I keep talking about dust. Dust is going to be heavier elements like carbon, oxygen, silicon, and iron. And it's going to have hydrogen compounds around it. And it's effectively going to be very small, like less than a micron in size. But they're effectively solid particles, as well as individual atoms. But what this does is the dust absorb, because it's made out of, tend to absorb and not re-emit very easily, or re-emit at very low wavelengths, very long wavelengths, low frequency, low temperatures. So you end up with dark patches where basically light doesn't come. At the edges, where you basically don't have as much material, you can see very dim stars around it. These are stars behind the cloud, not in the cloud. And you can see that they look redder because blue orb. The red light is going to get through more effectively. Effectively, blue light scatters and red light is going to scatter less. And infrared light will scatter even less. And so you can see through the cloud by looking at infrared light. And you can see the stars in and behind the cloud here. And they're still attenuated. There's still absorption. It's going to look redder, but you can now see them. And a new example here is a dark cloud of dust and gas. Looking in infrared, you'll see a revealed set, a newborn star and some stars in the background. And again, red light, completely different, and you can see the gas and dust structure around. And we zoom in, we can see the stars that are forming in this cloud. And the same sort of thing going on. We can see the star-forming regions in infrared light, where in visible light we wouldn't be able to see them. And again here for the Eagle Nebula. And so some explanation of what you're seeing in these pictures. You see dark invisible light gas, and the shape of the cloud is sculpted by other stars nearby that is heating up and causing the gas to disperse. In infrared light, the clouds become nearly transparent, and you can see the stars inside, and you can see the heating of the cloud, where thermal radiation is being absorbed and re-emitted. Right? So you can see the cloud as it evolves, as the new stars are being formed. So in general, the trend is that these dust grains are going to absorb visible light, which means they gain energy, they increase temperature, and then when they they re-emit that light corresponding to their temperature, which means it's generally much longer wavelength. And that's why we look in infrared light to see where stars are forming. We're looking for the heating of these clouds, which gives an idea of where the clouds are and what's inside of them. Right. So these clouds exist. Why do they turn into stars? Yeah, well, all matter by gravity. In these clouds, there's a gravitational force. There's also thermal energy, and that's going to press outwards just like it would in a star. Now, the gravitational energy is going to be low because the cloud is nice and big and everything's far apart. The forces between particles are low, and the thermal pressure is going to be low because it's a nice big cloud. If it becomes unbalanced for some reason, then it can contract or expand. And so, to become unbalanced, the cloud has to radiate some of its energy. It has to, effectively, emission lines have to carry away some of the energy from the cloud by changing the thermal energy into light. One way it can do that is if you have a neutral hydrogen atom, the different possible states are in just a single, one electron, one proton. State is both electron and proton are spin up. One is one up, one down. And one of these has a slightly higher energy. And if it can flip, which it's perfectly allowable to, if you remember the quantum mechanics, what things are and are not allowed, this sort of flip is allowed, and it allows a little bit of radiation to be emitted. And that happens to be in a particularly nice place for us to look at. What's called the 21 centimeter line. This is about, it's along the lines of the radiation from your cell phone. It's a little higher, I think, but around that. So electron flips, it'll give off a fairly long wavelength, fairly low energy, low frequency, comparatively, radio wave. And so it slowly can emit energy. Alright, so one of these clouds that we're looking at, a typical density and a typical temperature, for gravity to win out over this pressure, you're looking at a few hundred solar masses of stuff. And in general, you need even more if there's other. There can be magnetic forces. You can have higher kinetic energies as a group, as the gas is turbulent and it moves around. So, you need a fairly massive cloud, which means a fairly big cloud. We're talking on the order of light years across. But eventually, gravity can win out in a small, reasonable area, and it starts contracting. As it contracts down, it'll heat up. So, in some places in the cloud, this can happen, and you end up with a cloud fragmenting into smaller parts, and each of those small parts can form a star. Right. Here is a simulation of the cloud at the beginning, and after it's contracted a bit, you see it becomes lumpy and filamenty. And each of these sort of yellow segments in here can contract star, so you can get a little cluster of stars. This tends to be why stars occur usually not by themselves. Smaller clouds can maybe form a single star, but generally you get large clouds that form whole clusters of stars. So if the cloud happens to be unusually dense, that's a case where you can have the entire cloud collapse at once. So this brings us to an interesting bit here, is we can distinguish the very first stars from more recent stars. And the idea is what's in the original clouds. The very first stars are going to be almost completely hydrogen and helium, which means the processes that radiate energy away are going to have to deal with them, which means that there's less ways for the cloud to radiate away energy. The newer clouds, the more recently formed clouds, will have carbon and oxygen, and will have, in particular, carbon monoxide as a way of cooling the star. The clouds now can radiate away energy starting at a lower temperature. Before, the very first clouds only have hydrogen and helium, so that means that the clouds have to be larger to start contraction, which means that the clouds will form more massive stars. We think the very first stars were particularly more massive than stars now. The trend now, when we look at star populations, is mostly small red stars and a few large ones, a few large blue stars. But we think that stars in the early universe were larger and bluer as a population than they are now. So the very first stars we figure will be on the order of 100 solar masses, and that's because the molecular clouds were around the order of 100 Kelvin and never cooled below that. So they have to be very large clouds collapsing. Now, if the cloud collapses, if you think of a star, fusion stops in it or slows for it a bit. It cools, and then it contracts and heats back up, and the fusion rate picks back up. Is that the star has a steady state, or at least it has a feedback mechanism. Clouds appear to have that too. As the cloud contracts, it heats, and then eventually that temperature at thermal pressure is equal to contraction, and so it stops contracting. So the contraction will slow, right, as thermal energy builds up, and the center will form an object, what's called a protostar. The outer materials may not be in balance, but this local object that's kind of warm and dense will be stationary, so it'll stop contracting. But the general idea is, as it contracts, it heats up again. So the contractions only occur when the cloud can radiate away some thermal energy. So the growth of the star occurs when how much of the cloud outside of the protostar can fall onto it and make it a larger object. And so we can see that sort of contract. Now, other is basically wind and push away gas. Either the new star or neighboring stars can strip gas off of the cloud. So this process of it contracting and growing as more stuff falls inwards will eventually stop. It'll eventually run out of material. So, uh, excuse me a minute. So, as these clouds contract, you also flatten down. Is that, particles in the cloud are moving randomly, but eventually, if there's any sort of overall angular momentum, that gets conserved, and then the cloud is effectively all rotating in one direction. And so you get small flat disks. And so that causes the rotation of the star, is that the original rotation of the cloud will cause the star and the disk to be flattened, rotate and to form a disk. In these images, we can see there's different stars, and we can identify disks that are orbiting the, say, right here you can see, following the pointer, a disk there, and you can kind of see the dark disk. You can see these dark disks, and you can kind of see the, where you're seeing, a light point, you can kind of see the area around it. And in some cases, you can see the disk. You're essentially seeing light off of it and light reflected and emitted from it. In other cases, the disk is dense enough that it blocks the light internal to the disk, the star that's forming, and the glowing material in the interior of it. And here are some more disks you can see. I said this in the first week or so, and it's still true. The universe shows a lot of small flat disks. Here's another, let's say, rings around a star in this case. The rings are probably indicating that there are places where the planets are possibly forming and clearing their orbits. Rotation will also, on occasion, cause jets of matter to shoot along the rotation axis. It's not completely clear what that is, but lots of times when we see rotation disks, we also see those jets of matter. My cats are starting to crawl over me. How interesting. Here we see those jets, and we see the evolution of them over time. Right here we see them in visible and infrared, let's say. Here we see them in infrared, and they're flowing out. You can see the flow of matter outwards. Right, and then we can see some more images of, I'm not sure what exactly this is. Anyway, so we have an object that is getting denser and denser, and in general it is heating until it becomes stable. At some point, that heating is going to start nuclear fusion. So we want to know, how does it start? In general, the initial heating of a protostar, that initial thermal energy is coming from the contraction. It's not self-produced, it's the original energy of the cloud. And so that contraction has to continue until it gets hot enough. So the star is going to continue contracting until somewhere deep in the core, fusion, that temperature and pressure is high enough for fusion to start. So we showed these HR diagrams in the past. If you follow the pointer that's on the right, the initial cloud would be at the very bottom of the image, well off of the diagram that we first showed. And as the protostar forms, it'll get warmer and warmer. It'll move up and to the left until it enters the image. and then eventually it'll enter the main sequence as fusion starts. And for different masses, you can see on the left the sort of entry onto the main sequence for different masses. That final collapse of the protostar that kicks off fusion in the core will be these different curves. You can see it for a very small star. It's not very much heating, as a lot more contraction, not very much heating. For a large star, 100 solar masses, basically the energy output is pretty constant and the temperature rises. There's a much larger thing contracting down. Effectively, the luminosity, and the temperature grows because the particles are getting closer together. That gravitational energy is turning to thermal energy, and the more thermal energy you have, the more energy is radiated away, so the luminosity grows, and that's an unsustainable process until fusion starts. Then you can replace that contraction with energy from fusion. Right, so going through step by step. The initial cloud contracts, luminosity and temperature grows. At this point, the surface is looking like a star, but the interior is not dense enough, and the interior is not hot enough. And so energy is being carried from the core outwards by convection. And then at this point, at dot 3 here, the luminosity is nearly constant. You're producing as much energy as you lose from contraction, and radiation is carrying the energy through the star. And then eventually that temperature rises in the core high enough and fusion occurs. And now it's self-sustaining. It no longer need contraction, and you have enough energy to stop the contraction. So the is, comparing to the sun we figured took about 30 million years to go from a protostar to the main sequence. Smaller stars take longer because the process is effectively slower. You're dealing with less mass to move and less energy to radiate away, and so it can do it at a slower rate. Whereas in a higher mass star, the forces are a lot larger and it occurs quicker, on the order of up to tens of thousands of years. So this is where we get to the limits. Two things that can stop the contraction of a protostar. One is fusion kicking off. The other is degeneracy pressure. I mentioned that, and that's the next slide. Fusion will occur if you can get to about 10 million Kelvin before contraction stops. Contraction stops and it's not hot enough, you don't get fusion. It can't be thermal pressure because it's thermal energy. But degeneracy pressure can stop it. And you remember from the quantum mechanics chapter, this is just, you can't put the particles close enough together. You have to leave particles to not be in the same state. And so, as a comparison, thermal pressure is just the collision of particles with each other. It's the amount of heat in the particles causing the cloud to press outwards. Degeneracy pressure doesn't have any heat benefit. It doesn't have any relationship to heat. So if you reach degeneracy pressure, if you reach the point where that is a factor, you don't have any more heating because you no longer have contraction and you're radiating away thermal pressure. So degeneracy pressure kicking in is when it starts to cool instead of heat up. So what we find is objects that are larger than about solar masses generally have fusion in cores. Below that mass, you get an object that looks like a star, but degeneracy pressure is holding it up, and so it's cooling off. So these are objects not massive enough to start fusion, so they're dwarf objects, they're small, and we call them brown because they're dimmer than red objects. Right? The minimum size stars are red, and so dimmer than that is brown, so we call them brown dwarfs. And they emit light, they emit infrared light because it's the energy remaining after contraction. It's not newly produced energy, so it will dim. Its luminosity will go down over time. You can find them when they're still relatively warm and luminous. We've got an image here, and all the circles are where brown dwarfs appear to be. And you can see some of them in the image. You can see the dots where they are, and in some of them you can't. And so here's an image. You can... I think that's the same image, yeah. So you can see a lot of these objects that are glowing are probably brown dwarfs. So what's the greatest mass that a star can have? So going back a bit to this chart, we said that there was a limit of about 150 solar masses, and what's going on in these stars is as the star forms, the more massive stars are contracting faster, have a higher gravitational force, and that means they get a higher thermal energy, and that has to be radiated away faster, and the whole process speeds up. So for massive stars, there's a limit to the size of the star because of the amount of energy that's produced. And the process looks like the photons are just pushing the matter away. Effectively, photons can apply a small amount of pressure. They can put energy into an object when they're absorbed. So, very massive stars produce so many photons that collectively they're a fairly big push outwards, and they drive matter back out into space. So that kind of limits how big a star can be. Now, the actual size, the actual value of that limit is kind of hard to speak of. This radiation pressure seems like it would limit at about 150 solar masses. But when we set that limit, then we observe something that breaks it. So maybe those stars that break that limit, maybe they're forming from collisions between two massive stars. We're not certain, but you can calculate this radiation pressure for a given mass, and it becomes evident that there has to be an upper limit, and 150 solar masses is a reasonable estimate for that limit. So the gist of the range of stars, less than 8/100ths of the sun's mass, you get objects that can't start fusion. That's a hard limit. And then above 150 solar masses, you get lots of radiation pressure that pushes matter away. And ends up, if you have an object that's larger than that, a cloud will form a larger object, it'll push matter away and drop it below that limit, we think. Again, there might be mechanisms that allow for higher mass stars to form, but because we do find them, it's just a matter of our understanding of how that happens. So, what does a typical star look like? Here we have a plot of, kind of bending them up into low mass, sun-like masses, intermediate and heavy stars. And for, every one heavy star, you get, say, 10 intermediate and 50 sun-like stars and 200. This is a model. Is you're going to get, for every big star, you're going to get a lot of small stars. And so your typical stars are going to be small. And in general, when we look at star clusters, star formation seems to make a lot of low-mass stars and not so many high-mass stars. And that's what we see in the universe, is there's a lot of smaller red stars and fewer large blue stars. Some of that is that the universe is producing more red stars than blue stars. So that concludes chapter 16. If you're watching this, please note that later chapters I've already recorded. They typically aren't all in one go. There's several videos. I'll try to link those to you. When I need to record a new video, I'll record it and upload that. But if you're looking for videos and you can't find the newest one, go back in the old one, say 100, 150 videos on the YouTube channel, and you'll see videos for chapter 17 and 18 and so on. So I'll try to link those to you when I need to use those. But if you have any questions about this stuff, please email me. I hope this is helping for people that are using it, watching the videos. Let me know if you need anything, okay? Let's turn the pointer off and quit this thing.